So today we are going to see the kinetic energy of a rotating body and the concept of moment of inertia. Okay, so let's suppose we have this body and this body is rotating about some axis. Okay, it's rotating about this axis. Okay, in anti-clockwise sense, let's suppose. So different particles within this body, they will perform circular motion. So let's suppose there are n number of particles. So this particle has mass m1. It moves in this circle, okay, whose radius is, you can say, r1. Then this particle whose mass is m2, it moves in this circle whose radius is r2, and so on and so forth. Okay, so if we add kinetic energies of all these particles, we should get kinetic energy of body, right? So I can say kinetic energy of this rotating body, kinetic energy is equal to half of m1 v1 square. This is kinetic energy of first particle, plus half of m2 v2 square. This is kinetic energy of second particle, plus so on and so forth up to plus half of mn vn square. This is kinetic energy of nth particle. So if I add these kinetic energies, then I get kinetic energy of the body. Okay, then I can use this relation that v is equal to r times omega, and omega is same for all these particles because these are particles within the body. So the angular velocity of all these particles is going to be same, right? Angular velocity of all these particles will be same, and that means we can write v1 equals to r1 multiplied by omega, v2 equals to r2 times omega. Okay, omega is same for all particles. All particles will revolve through the same angle in same amount of time. Okay, otherwise there will be change in the shape of body, right? If particles revolve or particles rotate through different angles, then some particles will move ahead, some particles will be left far behind. Okay, so there will be change in shape of the body. So omega is same, right? So we can say kinetic energy is equal to half of m1 r1 times omega square, plus for second particle it is half of m2 r2 times omega square, plus so on and so forth up to plus half of mn rn times omega square. And what can we do is we can take half common from all of these terms, then we can take omega square common. So what are we left with? m1 r1 square plus m2 r2 square plus so on and so forth up to plus mn rn square. Okay, this thing multiplied by we have omega square, right? So see, this equation is the equation of kinetic energy of a rotating body, and this equation has a form of half of m into v square, right? So if we replace the velocity with its analogous quantity in rotational motion, then we get this term. Okay, this term has to be the analogous quantity of mass in the rotational motion. Okay, so analogous quantity of velocity is angular velocity. So this term we denote it by I. This is called as moment of inertia. Okay, so what is moment of inertia? So this equation can be written as kinetic energy equals to half of this term, which is, we can write it in short form or using the symbol, summation symbol. I goes from 1 to n, summation of mi ri square, and this thing is known as the moment of inertia. Okay, this term is known as the moment of inertia. So see, kinetic energy is equal to half of this term multiplied by omega square, or we can write this as half of I multiplied by omega square. So what is I? Where I is called as moment of inertia. It is called as moment of inertia. And what's that? So I is equal to summation of I goes from 1 to n. Okay, the small I goes from 1 to n of mi ri square. Okay, or you can say it is m1 r1 square plus m2 r2 square plus so on and so forth up to mn rn square. So see this kinetic energy of rotating body, it can be written like this: half of I into omega square. So compare this equation with kinetic energy in linear motion. So kinetic energy in linear motion. So it is half of m into v square, right? For linear motion, linear velocity is same for all the particles, right? For rotational motion, the analogous quantity of linear velocity is angular velocity. So angular velocity is same for all the particles in rotational motion. Okay. So we replace v by omega, right? Then comparing these two equations, we get a hint that analogous quantity of mass in rotational motion is this term I, which is summation of mi ri square. Okay, I goes from 1 to n, and it is known as the moment of inertia. It is known as what? The moment of inertia. Okay, so in linear motion, what is measure of inertia of a body? It is mass of the body, right? In linear motion, mass measures the inertia of a body. So similarly, in rotational motion, the measure of inertia is this term, the moment of inertia. Okay, so let's suppose, for an example, so let's suppose we have this very thin rod, okay, and it is very light, almost negligible mass. So at the ends of this rod, we have two masses. Okay, two masses are connected, m1 and m2, or let's call these two masses are m and m only. Okay, these two masses are equal. Okay, m1 is equal to m2, it's equal to m. So length of this rod is suppose L, and I want to find out the moment of inertia of this rod about this axis. Okay, about this axis. So how much is this length? So this much length is suppose L by 3, and this much length will be then the remaining L minus L by 3, right? So it is 2L by 3. Okay, so what would be the moment of inertia of this system about this axis? So it's very simple. We have our formula I is equal to summation of mi ri square. Okay, and what is ri? So it is distance from axis of rotation. So it is m1 r1 square, you can say, plus m2 r2 square. Here we have only two masses. Okay, so it is equal to, so we said that m1 is equal to m2 is equal to m. So it is m multiplied by how much is r1? So it is distance of mass m1 from the axis of rotation, L by 3. Okay, so L by 3 square plus m2 is also equal to m. So m multiplied by this, sorry, 2L by 3 square. Okay, so this is equal to what? M multiplied by L square by 9 plus it is m multiplied by, this will be 4 times L square by 9. So then ml square you can take common. So it is 1 by 9 plus 4 by 9. How much? 5 by 9. So moment of inertia of this system is 5 by 9 ml square. Okay. So this is how we can find out moment of inertia if we have some discrete mass system. Discrete mass system meaning we can measure the masses. Okay. One object or one particle, two particles, three particles, 10 particles, we can measure, if we can measure the number of particles, okay, then this is the way to find out the moment of inertia. If we have countable number of particles, right? So is it clear? So then let us talk about the moment of inertia of a continuous mass system. So like we have body which is like this. So here we assume that number of particles is countable. But for a rigid body, for a solid body like this, it's not possible to count the number of particles. So what do we do instead is, for this kind of body, okay, for this kind of body, can be anything, a potato, okay, or a cell phone, right? It can be anything. For any solid body, okay, we consider that the mass is uniformly distributed. The mass is uniformly distributed. So suppose I want to find out moment of inertia of this body about this axis of rotation. So this is the axis of rotation. So we break this body into n number of small masses. Okay, we call all those masses as dm. So let's suppose this much mass is dm. Then we find the moment of inertia of the small mass. So the distance of this mass from the axis of rotation is r. Okay, so what will be moment of inertia? So moment of inertia of small mass dm is, let's call it di. So it is r square multiplied by dm, right? It is r square multiplied by dm. And then we do it for all the masses, all the small parts, okay, all small pieces of mass dm over this body. So this procedure is called integration, right? This procedure is known as integration. So moment of inertia of this body, okay, of continuous mass distribution, distribution. Suppose I, it will be integral of r square dm. First one, for an example, I want to find out the moment of inertia of a thin rod like this pen. Okay, the moment of inertia of a thin rod about an axis which passes through its center of mass. Okay, about an axis which passes through its center of mass. So let's consider a thin rod. Let's draw a thin rod like this. Sorry. So length of this rod is L. So its center of mass will be where? It will be at distance of L by 2, right? Symmetry tells us that its center of mass will be at distance of L by 2. So let's consider an axis of rotation which passes through the center of mass. So this is the axis of rotation. Okay, so let's suppose this is the center of mass. This point is center of mass. So distances towards left, I will call them negative. Distances towards right, I will call them positive. So the position of this point is minus L by 2. Position of this point is L by 2 because total length is L. Okay, so suppose this rod rotates about this axis of rotation and I want to find out moment of inertia of this rod about this axis of rotation. Okay, so what do we do? So we have solved similar problem, right? Not for moment of inertia. So earlier when we discussed the center of mass. Okay, so what do we do is we consider uniform mass distribution and we consider that the mass of this rod is uniformly distributed all over the length of the rod, because this is linear body. Okay, so let's suppose the linear mass density mu equals to mass per unit length. Okay, so now we break this rod into n number of small chunks, small segments. So let's consider a segment. This is the small segment of this rod. Suppose it is at some distance. Let's call the distance x. Okay, this much distance is x. Okay, from here to here, and the length of this segment is dx. Length of the segment is dx. So mu is mass per unit length, right? So for this much length, I can say mu is equal to mass of this small chunk, okay, small segment, okay, which is dm, divided by its length dx. So then I will take this dx on other side. So I get dm is equal to mu times dx. Right, dm is equal to mu times dx. So the moment of inertia of this segment of mass dm is what? So mass of this segment is dm. So moment of inertia of the segment dx is what? dm multiplied by its distance square, where its distance is x, right? Its distance from axis of rotation is x. Okay, so dm multiplied by x square, right? So this is di. Okay, so see here we have got two variables. One is mass of the segment, right? One is mass of the segment, and the other variable is distance of segment from the axis of rotation. Okay, both of them can change. If you consider small segment, its mass will be small. Okay, if you consider large segment, its mass will be more, right? Second is the distance. So distance can change from where to where. So you can say it changes from, or you can say the position, it changes from minus L by 2 to plus L by 2, right? It changes from minus L by 2 to plus L by 2. Okay, so then you can integrate this, but before that we'll convert this dm, okay, in terms of dx, right? So it is mu times dx, we know. Okay, so di can be written as, using this equation, dm is equal to mu dx. It is mu times dx multiplied by x square. Okay, so now we have only one variable, x is the only variable, right? So now we can integrate this. So therefore the moment of inertia of rod, okay, about the axis passing through center of mass, about the center of mass, is I equals to integral of mu x square dx from where to where. So this x can change. X can change from where to where? From minus L by 2 to plus L by 2. Right? It can change from minus L by 2 to plus L by 2. So let's put that. Lower limit is minus L by 2. Upper limit is L by 2. Then we can take mu outside, because mu is a constant. So we take mu outside. So it is integral of x square dx from minus L by 2 to plus L by 2. And what is this integral? X cube by 3, right? We have this formula. Integral of x raised to n dx is x raised to n plus 1 divided by n plus 1. Okay, whatever are the limits, right? Lower limit and upper limit. Okay, so here we have x raised to 2. Its integral will be x raised to 2 plus 1 divided by 2 plus 1, that is x raised to 3 divided by 3. So we have mu multiplied by x raised to 3 upon 3. Lower limit is minus L by 2, upper limit is L by 2. So then you can take this 3 outside, okay, and now I can replace this mu also, okay. So I will replace mu by m by L. So I have m upon 3L, and in bracket I have x cube. So it is L by 2 cube minus L by 2 cube, right? So what's that? L by 2 cube is L cube divided by 8, right? It is L cube divided by 8. So we have L cube upon 8 minus L cube upon 8, that is plus L cube upon 8. So it is m upon 3L multiplied by 2 times L cube divided by 8, or you can say it is L cube divided by 4, okay. And here if we divide L cube by L, we get L square, okay, and 4 3s are 12, and that's why you get this formula for moment of inertia. It is ml square divided by 12. So this is the moment of inertia of a thin rod about an axis which passes through its center of mass, or you can say the midpoint, okay. This is moment of inertia of a thin rod about an axis which passes through its center of mass, or midpoint, you can say, okay. So is it clear? Yes, no? So next we'll find out the moment of inertia of a thin ring about perpendicular axis which passes through center of mass, okay. Moment of inertia of a thin ring about perpendicular axis passing through center of mass, okay. So let's consider a thin ring like this. So suppose this ring is very thin, okay. The ring is very thin, and this is the center. So this axis passes through the center of the ring, okay. And then what you can do is you can break this ring into n number of small chunks, okay, into n number of small pieces, okay. So each piece has mass dm, and how much is the distance of this mass from center of the ring? So its distance would be equal to radius of the ring. So we can neglect the thickness because it is very thin ring, right? So it is at distance of r, okay. We'll consider that the ring is so thin that the inner radius and outer radius is almost equal. It is equal to r, fine. So the distance of this mass, okay, dm, from the center of the ring is r. So how much would be its moment of inertia about this axis, because this is the perpendicular distance from this axis, okay. So the moment of inertia of this mass dm from the axis of rotation, this axis of rotation. Oh, what did I write? About the axis of rotation, not from. Moment of inertia of dm about, okay, the chosen axis, about the axis, let's call it y prime, okay. Instead of writing every time about an axis which is perpendicular to its plane and passing through center of mass, let's name it, okay. So the moment of inertia di will be equal to what? Dm multiplied by r square. And then how much would be the moment of inertia of this ring? about the same axis. So moment of inertia of the entire ring about y prime is what? It will be integral of di. Okay, I equals to integral of di. That is integral of dm into r square. And here, now you can see r will be equal wherever you choose any mass, small mass on this ring, its distance from the center of the ring will be r. Okay, so r is constant. You can take it outside. Okay, whatever is constant, you can take it outside of the integral. So you have I equals to r square integral of dm. And what will be integral of dm? So it will be sum of all small masses over this ring. So if you sum up all small masses over this ring, you will get what? You will get the mass of the ring, right? So it is equal to mass of the ring. So I'm sorry. So what formula do you get for moment of inertia? You get, okay, r square multiplied by m, or m into r square. So how much is moment of inertia of a ring about an axis which passes through its center or center of mass and it's perpendicular to its plane? It is m into r square. Okay, mass of the ring multiplied by r square. You get this simple formula. Let's find out the moment of inertia of a disk about a perpendicular axis which passes through the center of mass. So let's consider a disk now. So this is a disk. Okay. So like very thin wheel you can say, or your CD, right? So it is some disk, very thin disk. So you want to find out its moment of inertia about this axis which passes through its center and it is perpendicular to its plane. Okay, it is perpendicular to plane of the disk, right? So what do you do? So what will you do is you can think of this disk to be made up of n number of small rings. How come? So you take very small ring like this. Okay, you take a ring like this. Then you take another ring. Okay, which is like this. Okay, then you take another ring surrounding that. Okay, so if you take rings which are touching each other, very small rings of very small thickness, they touch each other. Okay, and you start from radius equal to 0, almost 0, to radius equal to, and you go till radius equal to capital R, which is radius of this disk. So if you keep on doing this, if you connect all such rings, what will you get? You will get the disk, right? You will get the disk. Yes, no? Okay. So you can say you can cut out rings from this disk, right? So I can take some thickness, I can cut out this much portion. So what do I get? I will get a ring. Okay. So I take that ring, keep it away. Then again, I will cut out this portion. So I will get this second ring. Then again, I can cut out this portion. So I will get third ring. So if I take those rings and put them back in contact with each other, I will get back the get back the disk, right? So this disk can be assumed to be made up of small rings, rings of very small thickness. Okay, so let's suppose, okay, I will draw one such ring. So this is the ring. Okay, So let's suppose the disk is made up of, okay, let the disk is made up of rings, okay, and rings of very small thickness, very small thickness. And how much is their thickness? So thickness is suppose dr. Okay, so this much thickness is dr. Okay, and of radius r, you can say. Okay, so how much would be the moment of inertia of this ring? So mi of a ring, this ring which is shown here. So we know the formula. So let's suppose its mass is dm. Okay, so then dm multiplied by this r square. This is small r. Okay, dm multiplied by r square. Can you see this? Okay, so this is small r. So dm multiplied by r square will be its moment of inertia. Let's call it di. It is dm multiplied by r square. So now again, once again, we have got two variables. One is dm, one is r. So what do we have to do? We have to convert dm in terms of r, okay, or r in terms of dm, whichever way. And then we can integrate it over the dimensions of this disk. Okay. So what do is we consider that total mass of this disk, because this disk has got some area. So we'll consider that the total mass of the disk is uniformly distributed all over the area of the disk. Okay, so we consider the total mass is distributed uniformly all over the area. Okay, so we define mu equals to mass per unit area of the disk. That is, it is m divided by how much is area. So this is circular disk, so its area is pi r square, right? So now my question is, how much would be the area? Okay, how much would be area of this ring? Who can tell? If I cut this ring over here, okay, and unwind it, what will I get? I will get a straight rod, you can say. Okay, so I will get a rod like this. How much would be the length of that rod? How much would be length of this rod? So the radius of the ring is r. Whatever is circumference of this ring, if you cut it from here and unwind it, you will get a rod, right? So whatever is the circumference of ring, that much would be the length of the rod, right? Yes, no? Getting it, everybody? Okay. So its length is equal to what? Its length is equal to 2 pi r. This much is length. And how much is thickness? So we are saying this thickness is dr, right? This thickness, okay, this thickness is equal to dr, okay. So this thickness multiplied by this length, this much would be the area, right? So this thickness is equal to dr. So this thickness multiplied by this length is the area of the ring, right? It's area of this ring. So let's suppose area of the ring dA is area of ring. So it's equal to 2 pi r, the length of the ring, multiplied by dr. And therefore, how much would be its mass? So mass of ring dm will be equal to what? So we have defined this quantity mu, which is mass per unit area, or you can say it is areal mass density. Just like we have linear mass density, this is areal mass density. Okay, so you can write mass is equal to mu times area, right? So this mass of the ring is mu multiplied by area of the ring, which is 2 pi r multiplied by dr. Okay, and then we can substitute this into this formula. So we get di equals to dm into r square, di equals to dm, which is mu multiplied by 2 pi r dr multiplied by we have r square. Okay, so this is moment of inertia of the ring, right? So now we can multiply this r with r square, so we'll get r cube. So it is 2 pi, so 2 pi multiplied by mu multiplied by r cube dr. This is the moment of inertia of the ring. So I want to find out moment of inertia of this disk. So what's my strategy to find out the moment of inertia? I have broken this disk into small rings, right? Rings of very small thickness. So if I connect all those rings, I will get the disk, right? So moment of inertia of a disk, so moment of inertia of disk will be integral of this di. I is equal to integral of di. So that is equal to 2 pi mu r cube dr, integral of this. So what's the variable? Small r is the variable. What is minimum value? Minimum value is 0. What is its maximum value? Maximum value is capital R, right? So then you can take 2 pi mu outside of this integral. So I can take 2 pi mu outside. So it's integral of r cube dr from 0 to capital R. And I know this integral. So it is integral of r raised to n will be r raised to n plus 1 divided by n plus 1. So this is r raised to 4 upon 4. And since lower limit is equal to 0, it is just capital R raised to 4 divided by 4, right? So we can substitute that. So we get 2 pi mu multiplied by r raised to 4 divided by 4. Okay, and then we can substitute what is mu. So mu is pi r square. Now before that we can cancel out this. Okay, we can divide this 4 by 2, so 2 will remain in the denominator. Okay, and then we can substitute mu is equal to pi into r square. Sorry, mu is equal to what? M upon pi r square. It is m upon pi r square. So let's substitute that. So we get I equals to pi multiplied by m divided by pi r square multiplied by r raised to 4 divided by 2, because we divided this 4 by this 2. So this pi and pi gets cancelled out. R raised to 4 divided by r raised to 2 gives us r raised to 2. So the moment of inertia of a disk, very thin disk, about an axis which passes through its center of mass and it is perpendicular to its plane, is mr square divided by 2. This formula also we have to memorize. So let's see this problem. A circular disk is to be made by using iron and aluminium so that it acquires maximum moment of inertia about geometrical axis. Geometrical axis meaning which axis? The natural axis. Okay, so for a disk it is an axis which is perpendicular to the plane as we have seen and passing through its center of mass. Okay, it is possible with option A, aluminium at interior and iron surrounding it, iron at the interior and aluminium surrounding it, using iron and aluminium layers in alternate order, and sheet of iron is used at both external surface and aluminium sheet at internal layers. We know that aluminium is very light compared to the iron. Okay, so now the formula of moment of inertia is what? For a disk, you can say it will be integral of dm into r square. Okay, this is the formula for moment of inertia. So as far this mass is from the axis of rotation, moment of inertia would be more. Okay, so if you keep heavier mass away from axis of rotation, because it's directly proportional to r raised to 2, right? So if you keep heavier mass away from axis of rotation, the moment of inertia will be more, and that means you have to keep iron away from axis of rotation and aluminium closer to the axis of rotation. Okay, so which is the answer out of this? It would be this one, aluminium at interior and iron surrounding it. You got this? Yes, no? Let us see next one. Flywheel rotating about fixed axis has a kinetic energy of 360 joule when its angular speed is 30 radians per second. The moment of inertia of flywheel about the axis of rotation is. Again, very straightforward, very simple question. The kinetic energy is equal to what? Half of I multiplied by omega square. Okay, let's call it Ke or just K. So it is half of I into omega square. And you want to find out I. So move that 2 and omega square on the other side. So I will be equal to kinetic energy 2 times kinetic energy divided by omega square. Right, this will go in denominator and this will go to the numerator. So now we just have to put the values. So it is 2 times 360 divided by 30 square. Okay, so 30 square is 900. Okay, so it is I is equal to 2 multiplied by 360 divided by, you can say it's 9 into 10 raised to 2. So 9 fours are 36. So this will be 40. Okay, 42 are 80 and 10 raised to 2. Take it to the numerator. It will be 10 raised to minus 2. So how much? 80 multiplied by 10 raised to minus 2 or 0.8 you can say. Okay, 0.8 kg meter square. This is the answer. Option C. Okay, right. Let's see next one. So this question, in a rectangle ABCD, BC is equal to 2 times AB. Okay, so this length BC is equal to 2 times AB. The moment of inertia is minimum along axis through. So tell me, which will be the answer? It's a very simple question. If you want moment of inertia, let's keep maximum mass closer to the axis of rotation. If you want moment of inertia to be more, keep maximum mass away from axis of rotation. So see, if you take this axis, okay, for an example, this axis, if you take, so there is more mass away from the axis of rotation, right? This length is more, so that means there will be more mass away from axis of rotation. But if you take, okay, uh, what are the options? HF is there, which is HF, this one. Okay, so since for this one, this length is more, okay, compared to you take this thing, okay, if you take BC, so this length is, it would be smaller. Take BD, where is BD? Okay, this is diagonal, so this length would be more. So for this one, the moment of inertia would be more. Then you have EG. So which is EG? This is EG. So now if you take this axis, okay, so mass is distributed at minimum length from this axis, you can say. Yes or no? So moment of inertia will be least for this axis, minimum for this axis. Okay, so this is straightforward. Answer of this question should be EG. The ABC is a triangular plate of uniform thickness. So this is triangular plate of uniform thickness. The sides are in the ratio as shown in the figure. It's the same ratio, right? 3, 4, 5. Okay, it's the same ratio as that of last question. IAB, IBC and ICA are the moments of inertia of plate about AB, BC and CA respectively. Which one of the following relations is correct? Okay, IAB plus IBC is equal to ICA. Okay, then next is ICA is maximum. Is ICA maximum? No. IAB, which is IAB, this is IAB, is greater than IBC. No. Okay, so IBC is greater than IAB. So this one is correct, right? It is straightforward. IBC is maximum. So IBC is greater than IAB because mass is at maximum distance from this axis BC. Okay, so this one is correct. Option D is the answer. Okay, see this. Three particles, each of mass m gram. These three particles are situated at the vertices of equilateral triangle. This is an equilateral triangle ABC of side L centimeter as shown in the figure. The moment of inertia of system about line AX. So AX, we want to find out moment of inertia of these three masses about this line AX perpendicular to AB. So this is perpendicular to AB and in plane of ABC. It is in plane of ABC. In gram centimeter square units will be. So very simple and straightforward, right? So how much will be moment of inertia? I equals to, you can say, for this mass, it is on the axis itself. Okay, so m multiplied by 0 square. For this mass, it is m multiplied by, okay, m multiplied by L square. Length is L. Okay, so m multiplied by L square plus for this mass. So how much would be this distance? If this is an equilateral triangle, so if you draw a perpendicular from here, okay, if you draw perpendicular on this line from here, it will meet at L by 2, right? So its distance is L by 2 from axis of rotation. Okay, so its distance is L by 2. So it is m multiplied by L by 2 square. Okay, so this thing is 0. ml square plus this is ml square by 4. Okay, ml square plus ml square divided by 4. And you can make denominators equal. So you can multiply and divide by 4. So this will be 4 ml square by 4. So 4 plus 1 ml square by 4. So that is 5 ml square by 4. This is the answer. Option C is the answer. Okay, very simple question. Is it clear? Or there is a doubt? A light rod of length L has two masses m1 and m2 attached to its two ends. The moment of inertia of the system about an axis perpendicular to the rod and passing through the center of mass is. Okay, so there is a light rod, that means we have to neglect its mass. Okay, so this is the light rod and there are two masses m1 and m2. Okay, at the two ends of that light rod, and we have to find out moment of inertia of this system about an axis which is perpendicular to the rod and passing through what? The center of mass. So let's suppose, okay, m1 is greater, the center of mass would be towards m1, right? So let's suppose this is the axis which passes through center of mass. So this much length is suppose L1, this much length is suppose L2. So L2 will be equal to what? It will be L, the total length, minus L1, right? Okay. So we can find out L1 and L2. So how much will be L1? So it is distance of center of mass. So this point is center of mass. Okay. So it's distance of center of mass from M1. Okay. So how do you find? So we can start counting distances from M1. So we can say, how will you find center of mass? From M1. Okay. So that length is, that distance is, sorry. So distance of center of mass from M1 is L1. So that is equal to M1 into 0, right? Plus M2 multiplied by, so from M1, M2 is at distance of L. So M2 into L divided by M1 plus M2. Okay, it is M2 times L upon M1 plus M2. That's L1. Similarly, you can measure the distance of center of mass from M2 also. So it will be, okay, just replace M1 and M2. So what do you get? Similarly, distance of center of mass from M2, which is L2, it will be M1 times L divided by M1 plus M2. Or you can find this distance like this also. So L2 will be equal to this total distance minus L1. Okay, so L minus L1, but that would be wastage of time. Okay, as you would put L1 equals to this thing M2 into L upon M1 plus M2. Then you have to make the denominator same, and then you have to do subtraction. Okay, so we'll use our common sense. We'll just exchange M1 and M2. So we'll get L2, distance of center of mass from M2 will be equal to what? It's L2, so it is M1 divided by M1 plus M2 multiplied by total length. Okay, just like distance from M1 is M2 multiplied by, M2 divided by M1 plus M2 multiplied by length L. Is it clear? Everybody? Okay. So now that we have got distances, how much is the moment of inertia? So let me add a page here. Okay. So how much would be moment of inertia? So moment of inertia I is equal to m1 L1 square plus m2 L2 square. Let's put the values of L1 and L2. So we get m1, L1 is m2 into L, m2 times L upon m1 plus m2, and you have square of this whole thing, plus you have m2 multiplied by m1 into L divided by m1 plus m2 whole square. Okay, then you can square, so it will be m1 m2 square L square. So this is m1 m2 square L square, and in denominator of both of these you have m1 plus m2 square. So plus you have m2 multiplied by m1 square L square. Right. So now what you can do is, you can take something common. You can take L square common from both of these terms, and also you can take m1 m2 common. Right. So what will be left from first term? M2 only, and from second term M1 only. So you get M2 plus M1. Okay, so this is what? M1 M2 multiplied by M2 plus M1 multiplied by L square divided by M1 plus M2 whole square. So you can see this thing and this square, gets cancelled. I mean, there will be m1 plus m2 left in the denominator. So you get moment of inertia I equals to m1 m2 upon m1 plus m2 multiplied by L square. So this is the formula that you get. Okay. So m1 m2 upon m1 plus m2 L square. Option A. Okay. And now, see, we will memorize this formula also. This is the moment of inertia of two masses. Okay, two masses about the perpendicular axis which passes through the center of mass. Okay, moment of inertia of two masses about an axis which is perpendicular to the line joining two masses and which passes through the center of mass. So it is m1 m2 divided by m1 plus m2 into L square. Okay, and this thing is called as the reduced mass. So got it? Yes, no? This thing meaning m1 m2 upon m1 plus m2 is known as reduced mass. So you get this formula I is equal to. So if you have two masses, okay, rotating about each other, okay. So we have seen system like this. So for an example, a double star system. We talked about double star system. So both of the masses actually revolve around what? Common center of mass. Okay. So for that system, you can say how much would be its kinetic energy. Kinetic energy will be equal to this moment of inertia. Okay, moment of inertia is reduced mass. Okay, mr, r for reduced, multiplied by L square. And how much is the reduced mass? So reduced mass is m1 m2 divided by m1 plus m2. Okay, so kinetic energy will be half of I into omega square, where I is what? mr, the reduced mass, multiplied by L square. So got this? Yes, no? So let's move on to next question. Two bodies have their moments of inertia I and 2I respectively about their axis of rotation. If their kinetic energies of rotation are equal, their angular velocity will be in the ratio. Okay, very straightforward, right? So kinetic energy is equal. So you can say kinetic energy of first one is equal to kinetic energy of second body, right? So it is half of I1 into omega 1 square equals to half of I2 into omega 2 square. Half will get cancelled, and it's given that I2 is equal to 2 times I1. So I2 is how much? 2 times I1. So you can divide this by I1. So 2 will remain there. So omega 1 square is equal to 2 times omega 2 square. Okay, this is what we have. And you want ratio of omega 1 to omega 2. So take that omega 2 on left hand side and take square root. So omega 1 upon omega 2 will be square root of 2 is to 1, you can say. Okay, so option C is the answer. Person of mass m and radius r rotates about an axis passing through its center and perpendicular to its plane with angular velocity omega. Its kinetic energy is. What's the answer? Tell me. Option Option A, right? Option A is the answer. Yeah, because moment of inertia is half of I into omega square, and for a ring, how much is the moment of inertia? Mr square only. So it's equal to half of mr square multiplied by omega square. Okay,